Modern data centers represent billions of dollars in capital investment, moving massive volumes of chilled fluid through highly complex mechanical networks. Yet, despite these resources, these exact facilities routinely fail to prove their efficiency during audits. This dashboard displays a 1.18 power usage effectiveness metric. A perfect score like this is meaningless if it lacks a documented physical boundary. This number is an illusion unless there is a direct, audited link back to the physical pipe. High-accuracy field sensors are useless if their support infrastructure fails. A precision instrument cannot compensate for dirty power, mismatched time synchronization, or a broken network connection. This diagram shows the 5-layer measurement architecture. True precision requires building a unified system that starts down at the physical field device and extends upward through power, edge control, and the historian, culminating in the final evidence pack. This flowchart maps the golden thread of traceability. For any recorded key performance indicator to be valid, it must trace back through a specific path, a declared physical boundary, a highly calibrated instrument, synchronized timestamps, strict quality rules, and a clearly declared uncertainty value. This table defines the explicit owners of those system boundaries. The designer sets the operating range. The installer preserves straight-run pipe conditions. The commissioning authority verifies calibration, and the operations team publishes the final metrics. A performance metric is not certified until all of these boundary owners jointly declare and verify the physical and mathematical rules governing it. The metric only exists when the evidence supports it. To see how this architecture is built, we start at Layer 1, the physical pipe. Here, control valve actuation sets the mechanical baseline. Motorized valves must stroke in under 30 seconds to strictly prevent hydraulic shock in these complex chilled water plants. This requires battery or capacitor spring returns and 0 to 100% dual potentiometer feedback to guarantee the valve's exact physical position. This graphic details valve actuation targets. When using pressure-independent control valves, you do not apply traditional authority equations. Instead, engineers must verify minimum operating differential pressure and ensure stable flow turndown. This schematic shows a complete BTU thermal metering system. Capturing certifiable thermal duty begins on the left, with an electromagnetic flow meter installed on a completely full pipe. The meter must be properly grounded, demanding strict adherence to specified straight-run lengths of piping. However, the stated accuracy of that flow meter alone is entirely insufficient to establish the uncertainty of the total thermal duty. This diagram calculates differential temperature using matched Class A platinum RTD sensor pairs at equal depths. Evaluating sensors as a matched pair tightens the uncertainty baseline compared to absolute individual readings. Splicing or mixing cable extensions permanently corrupts the baseline data. We now move to Layer 2. The precision generated by these physical devices is highly fragile and easily destroyed by electrical and cyber interference. This diagram outlines the instrument power and cabling requirements. The physical protection layer dictates redundant, UPS-backed 24-volt DC power supplies and twisted shielded pairs, strictly segregated from heavy motor power. It requires single-point grounds to eliminate loops that distort sensitive analog signals across the daisy chain. With the physical wiring secured, the vulnerability shifts to digital protection at the sensor edge. Moving to the digital protection layer, BACnet Secure Connect applies TLS encapsulation. This encrypts the data payload, defending the field instrumentation against man-in-the-middle cyber exploits. Layers 1 and 2 create a physically and digitally fortified measurement endpoint. Without this resilient foundation, all upstream data sent to the historian is mathematically contaminated before it even leaves the mechanical yard. At Layer 3, those protected raw field signals reach the edge controller, where they are converted into structured digital records. This panel defines edge data logging. A certifiable record must contain a timestamp, value, engineering unit, quality flag, and sequence number. The storage math example shows an edge controller must buffer 72 hours of data, requiring 16 gigabytes of storage to prevent loss. This illustrates historian recovery. During network failure, the system triggers an oldest first throttled replay of buffered data, prioritizing life safety points. Phase 4 uses idempotent upserts with strict merge rules to fill historical gaps cleanly without creating duplicate accumulations. The data finally arrives at Layer 5. The evidence pack, where recovered field telemetry is translated into the mathematics of certification. This slide details the mathematics of traceability. The top panels display core formulas for thermal duty and plant COP, whose variables must match exact boundaries. The lower panels outline uncertainty calculations, determining the total margin of error for the entire measurement system. This mathematical uncertainty dictates the ultimate decision rule for contractual project acceptance. This graph plots operating margin against expanded uncertainty. A facility cannot claim an operating capacity if it falls within its measurement system's margin of error. The true capacity margin must demonstrably clear this expanded uncertainty band. Data completeness and mathematical uncertainty govern the legitimacy of efficiency metrics. Without them, a dashboard is just generating uncertifiable numbers. We must also prove this architecture can withstand extreme edge cases and harsh physical environments that constantly threaten measurement integrity. This graphic highlights environmental extremes. In severe monsoons, outdoor transmitters need IP65 ratings, anti-condensation heaters, bottom cable entries, and 316 stainless steel to prevent corrosion. Inside, ASHRAE 15 protocols dictate life safety. Wall-mounted sniffers detect toxic leaks, immediately starting emergency exhaust and stopping protective equipment. This pyramid maps the facility control hierarchy. Life safety and equipment protection always hold supremacy over Tier 5 digital optimization. The base acceptance rule dictates every hardwired override must have a physical label, an alarm, and undeniable proof an unexpected automatic restart cannot occur. This workflow shows standard operating procedures for maintenance. Notice the critical SO key hold point. Automatic optimization remains inhibited until the restored device and its historian data quality are independently verified. Safety protocols and hardwired mechanical overrides always supersede automated efficiency systems. The local hardware retains final authority over the digital twin. This staircase outlines the commissioning path to bring the measurement architecture online, moving from initial design up through failure testing at level 5. Project turnover remains incomplete until all physical deficiencies are closed, temporary bypasses removed, and the evidence index is searchable. This matrix displays the final reporting gate for efficiency metrics like plant COP, PUE, and WE. It verifies no metric is certified unless its physical boundary, continuous 12-month interval, data completeness, and normalization methods are explicitly proven, with 0 unexplained gaps. True data center performance is never derived from the precision of a single sensor. It is the result of an unbroken, certifiable mathematical chain, stretching directly from the flow in the physical pipe to the final digital audit.